Hello, this is Lyndon, and I'm here today to present to you my project, Periodicity Detection of Quasiperiodic Audio Signals. My goal is to use digital processing techniques to compute measurements of consonance and dissonance in real audio samples. The main focus of my research was analyzing dyads, which refers to a set of two distinct pitches. For example, these are the dyadic intervals in a C major scale. Each one has a different consonant or dissonant sound to our ear. For example, the perfect fifth dyad has a much more consonant sound, while the major seventh dyad has a much more dissonant sound. One of the leading theories of the consonant's perception of sound is based on periodicity detection. Take this formula for a sound, where S is the function of the sound, A is the magnitude of the frequency, or its volume, omega is the frequency of the sound wave, and T is the amount of time passed. Sine just refers to how the frequency of a sound is normally represented as a sine wave. Stolzenburg originally used this function to study pure tones, which are made up of only one constant frequency. However, real instrumental sounds have many more frequencies playing at once along with their most audible frequency. Therefore, I adapted this function to consist of all of these additional frequencies. Here, each additional sine function represents an additional frequency of the sound. From here, we can apply the autocorrelation function to our sound wave, where rho is the autocorrelation function and tau is the phase delay, creating a variation of our original sound. We will get to this in a bit. First, each audio sample starts as a waveform of data. The graph shown on the right was part of a collaboratively written article, Relative Periodicity of Empirical Audio Samples with Application to Dissonance Perception, where we also test the same methodology on sample piano triads, which are sets of free pitches. Once we have our waveform of sound, attack and attenuation must be accounted for. Attack is the beginning of a sound, the time it takes for it to fully develop. For this waveform, the attack segment would be around here. Attenuation is the diminution of sound over time. For the purposes of my research, I have deemed the attenuation sections to be over here. However, it technically happens over the entire audio file. This leaves us with this sliver of time for us to analyze the sound. Now we have our trimmed window chosen based on the best perceived interval of sustained sound. Next, we must apply the autocorrelation function to our sound wave. Remember this formula from earlier. Let me explain it more in detail. Take this pure sine wave. Assume that this is our sound function. If we change the inside of the parentheses by a variable phase delay, this will move our sound wave to the side, as follows, where tau is the phase delay. This is the core of the autocorrelation function. We multiply our sound wave by itself shifted by a phase delay for all values of tau. If we link our sine functions to a graph, we can see that the product will vary for this phase delay. In this case, the majority of the products are negative, as one sine wave is often above the horizontal axis while the other is below. The important part is that we determine what phase delay results in the sounds overlapping again, where all the products between the two sine waves are maximized. This is how the autocorrelation function helps us determine the period of the sound. We find the phase delay that causes a maximum of the product, and tau represents the relative periodicity of the sound. Now that we have rho as a function of tau, we can run an envelope estimate to find its period. Look closely at the second peak on the graph. The envelope estimate will detect this peak and return its tau value in seconds. With this, we have successfully estimated the relative periodicity of the sound. Here is a sample of 4 graphs of the relative periodicities for 4 different types of dyads. My results support Stolzenburg's periodicity theory, especially for the more consonant dyads, such as the perfect fourth and perfect fifth. Additionally, there were also results that were significantly different, especially for the more dissonant dyads, such as the minor sixth and the tritone. This agrees with the work of Messina et al. Regarding how harmonicity alone cannot explain the dissonance of these dyads. The results of our investigation serve as a major stepping stone in studying the conception of real instrumental sounds and advancing the state of knowledge of psychoacoustics.